So Deborah talked a little bit about what you had already some ideas about how radial velocity signals are affected by noise coming from the star, and different techniques we can do to try to improve that. I will a little bit come back to the different type of signals that are affecting the radial velocity, trying to explain them to you. And of course, there is plenty of different type of stars with different spectral types, and all these signals that are affecting the radial velocity are different according to the different type of stars. So I will try to give you a little bit a sense of which stars are the best if you want to measure very good radial velocity with a very good precision. So I like a lot this movie of the sun. So this was taken in 2012 by the SDO satellite. And this is the transit of Venus back in 2012. So first of all, the thing that you see in this image is the size of the planet is really tiny compared to the size of the sun. So of course, if you want to start to detect this signal, then it starts to be a big problem. And in the case of Venus, you have a projection effect because we are close to the sun and Venus is close to us. So in fact, if you are thinking about a planet like Venus or the Earth around another star, it's even smaller than that. And here what you see is a big active region here. That it's in this case, it's a plage that you can see here. You see magnetic field that goes from one side of the plage to the other side here, and this evolves as a function of time. So because this region is much bigger than the planets, you can say that it can create an effect in radial velocity or in photometry that is bigger than the effect of the planet. So we need to understand that. So I will not speak about that. I showed it yesterday already. You have a planet orbiting around a star. The star will move a little bit. You take the spectrum. The spectrum will be blue shifted, red shifted, and you can detect if there is something orbiting around the planet. But then when you observe some radial velocity data, so these are all real data. In this case, it's not simulation or whatever. Over very long time scales, about 10 years, you see some drift in the radial velocity. And this is due to the magnetic cycle of the star that have a counterpart in the radial velocity. And I will explain why afterwards. Then you zoom a little bit in, and you observe several, in this case, 2 to 3 months of data. And this is what you see. You see some modulation. And this is due to the activity of the star, spots and facula, like rotating with the star. Then you go at shorter timescales, over the timescale of one night. And if you take really observation every few minutes, this is what you observed over the timescale of the night. You also see some variation there. And this is due to granulation, which is the convection of the star, because convection evolves as a function of time. And then on a very short time scale, then you see what we call solar oscillations due to pressure waves that propagate on the surface of the star, and therefore the surface just oscillates as a function of time, and you can measure this with the radial velocity. So this is the big picture that we have of the different signals that we can see in radial velocity. So here from very short time scale, less than 15 minutes, to, in this case, very long time scale magnetic cycle. And here you have different colors. Blue means that we understand the signal, and either we found already a good technique to mitigate the effect, or they are negligible. Like in the case of flares, the effect should be quite small, and mainly the main problem will be for active M stars that are late M's, basically. So for the moment, we don't have too much problem, but perhaps in the next coming infrared surveys, it will be they will have some problems due to flares. Then granulation, which is due to convection of the star. Then here, red active region, because it's really, I think, the biggest problem that we have so far. And as Deborah explained it to you already, for the moment, we don't really have good techniques to correct for the effect of active region. Then gravitational redshift, but it's an effect that is extremely small. And then magnetic cycle over the long term. But in the case here, it's green because we already have a few ways to correct for it. It's perhaps not perfect, but it's already a good start. So what we want to do when we observe a star with the radial velocity technique is find planets. However, if I just go back to the slide before, here I give you an idea of about the amplitudes of the effect that you're expecting. And you are more or less, for most of them, here meters per second. Here it can be up to 10, 20 meters per second. So if you look to the solar system, and you measure what is the amplitude that you expect, you actually calculate what is the amplitude that you expect from the different planets. Okay, so Mercury, 1 centimeter per second. Venus and Earth, 10 centimeter per second. And then Mars, it's even smaller than 1 centimeter per second. So you can forget about all these planets. So it's a big problem. If you have stellar activity and oscillation and so on, you cannot detect those planets. Okay. And then what about Jupiter? Jupiter is also a problem because, as I showed you before, the effect of magnetic cycle is over several years, and it can be 10 to 20 meters per second. And on the Sun, the magnetic cycle on the Sun is 11 years. And the orbital period of Jupiter is 11 years. So they are probably not in phase. So perhaps you can find a solution to decorrelate the magnetic cycle and the effect of Jupiter. But it can be a problem. And in fact, there is a few planets in the literature that have been published. And they are probably, long period Jupiter planet, and they are probably due to magnetic cycle and not due to real planets. Okay, so now let's go a little bit on each different stellar signals and try to understand where they're coming from and what we can do. So stellar oscillations. So all the stars that are like the Sun have a convective outer envelope where you have pressure waves that can propagate. And here you can see different types of modes of propagation of those waves. So this is Doppler map. So blue is blue shifted, red is red shifted. And all these modes, when you combine them all together, create some oscillation of the radial velocity with an amplitude of about 1 meter per second and a time scale on the Sun of about 5 minutes. So then I will show that if you go to different type of stars, then this time scale here change. Okay. But what can we do to mitigate the effect of stellar oscillation? So if in 5 minutes you have one oscillation, if you observe the star for 2 or 3 of this oscillation constantly, and then you just average out all the measurements you have. So it's like having a sine wave. You take all the points, you just take the average of this, it will be close to 0. So here you have the radial velocity RMS of the star, and here you have the exposure time of the measurement. So if you do very short exposure time, a minute, you are at about 50 centimeters per second due to the oscillation. And then if you increase your exposure time, you see that you go down quite fast. And basically, after 15 minutes, you're at a level that is smaller than 20 centimeters per second. So if you want to detect an Earth, it's still a big problem. But at least in our case, where we have a meter per second precision, we can just increase our exposure time, and we can mitigate the effect of oscillation. Then what about granulation? So this is a very high resolution picture of the Sun. I showed it already yesterday. And all what you see here, those bright cells, are just like bubbles of plasma that goes up to the surface of the star. And then around those cells, you have dark lanes here, where it's the flux that is cool, cooled down. So less temperature, so less emission. And so you really see this movement of the convection on the surface of the star. And this is not static. If you look to a movie of the Sun taken with solar telescopes, this is what you see. This evolves as a function of time, with a time scale of about 10 minutes. So a cell, you can see a cell, and then 10 minutes afterwards, either it disappears or it fusions with another cell, and so on. So you have an evolution time scale on this. So this is on very small scales, about 1,000 kilometers in this case, and short time scale, 10 minutes, half an hour, something like that. But then if you look to a Dopplergram of the Sun, at this is the entire solar disk, you see also some cells, blue shifted and red shifted. And then if you look to how those cells evolve, it's not super easy to see on this image, but also those cells evolve as a function of time with a time scale that goes up to 2 days. And more or less, you don't have this here 10 minutes and this here in 2 days, you have like a continuous thing between a few minutes to 1 to 2 days. So what can you do when you observe in radial velocity? So this is really simple, but let's say that so you have this variation as a function of time on a short time scale. So you have this sinusoidal signal. It's not sinusoidal, of course, it's more stochastic than that. But let's take observation during the same night with a spacing of 2 hours. So in this case, if you take measurement every 2 hours or every 1 hour, the thing is you will be at different phase of this signal. Okay. So then if you average out those signals, you are at something that is closer to 0 than just one measurement. Okay. Eric, you are looking. Well, okay. Then if you have long timescale signals, longer than your spacing between your measurement, and it's a sinusoidal, same thing, you will sample a little bit this signal, you take the average, you add something that is closer to 0. And so this is a test that we have done with HOPS. We have observed Alpha Centauri B, which is a very bright star, so we are not photon noise limited, nothing. And we tried different strategies to observe this star. So first of all, we tried one measurement per night, 15 minutes. So I told you that before we use 15 minutes, so we mitigate the effect of oscillation, okay? So basically all what you see here is mainly the effect that is due to the granulation in this case. So now let's try one measurement per night, but let's try to increase our exposure time to half an hour, okay? And you see that you decrease a little bit, but there is really nothing very significant there. And it's because after 15 minutes, you have averaged out the signal from stellar oscillation, and then you have the signal from granulation that is from a few minutes to 2 days. So you start a little bit to reduce the signal from granulation, but not so much. And then you take 2 measurements per night of 15 minutes, so the same total exposure time than here. And then you see that you drop in the radial velocity RMS. And then even if you take 3 measurements per night of 10 minutes, so still the same total exposure time, you can even decrease a little bit more. Okay. And so then there is another thing. So this is like taking several measurements per night can help you in mitigating the effect of granulation. And this here, it's the power spectrum, so the Fourier transform of different radial velocity sets of different spectral type stars. And so here you have the period, and here you have the power at each period, basically. So this bump that you can see here, it's the bump due to the stellar oscillations. And then this increase at low frequency is the signal due to granulation. And so what you see is that the curves that are on the top here are for G subgiants, and then the curve that is at the bottom here, it's a K-dwarf. It's Alpha Centauri B. And so you see two things. First of all, this peak here due to the oscillation, so the maximum here, just decreases, okay, in period. So basically, when you go towards K-dwarfs, the time scale of the oscillation goes from 5 to 10 minutes to something closer to 1 minute. So then if you observe a K-dwarf, you are not obliged to observe for 15 minutes. If you just observe for 5 minutes, it's enough. And then you see also that the amplitudes of the oscillation also goes down. So G-dwarfs are more affected by oscillation in radial velocity measurement than K-dwarfs. And then if you look to the level of the granulation that you can see here, you also go down. So basically the take-home message is K-dwarfs are less affected by granulation and by oscillation. And then if you go towards the M-dwarf regime, it still continues like this. Then in the M-dwarf regime, you have activity that is perhaps stronger. So this is another question. Okay. So now let's speak about the big problem that we have, active region. And I will not repeat everything because I already said something yesterday, but you are affected by two different effects, the flux effect, because a spot or a facula will have a different temperature than the photosphere, so a different contrast. And then the effect of convection, because inside a spot or a facula, you have strong magnetic fields. Those magnetic fields inhibits the convection of the star, so an active region is redshifted compared to the surface of the star. So this is the flux effect. You have this antisymmetric effect here, plus and then minus with respect to the center of the star. And then I just repeat this because I think it's important, this thing about the convective blue shift. So in this image, you see all the cells due to the convection of the star. And because you are sensitive to the flux, so to the brightness of those cells, what you see when you measure in radial velocity this part of the sun is only the bright cells. So only the cells that are coming towards you, towards the surface of the star. And because the velocity, the velocity of the convection is 300 to 400 meters per second, you see that all the surface of the star is blue shifted by this amount. And then if you put a spot, you put some magnetic field that inhibits the convection, and therefore a spot is red shifted compared to the photosphere. And you have these two different effects, plus minus effect due to the flux, and then this like symmetric effect with respect to the center due to the convection, and it's just because you just have a projection effect in this case. Okay. And now let's speak about magnetic cycles. Okay, so here on top, you have a measurement of the emission that you have in the calcium H and K line. So it's an indicator that we use to measure the activity of the star. And so if you look at this on the sun and you compare this log A image here, so this calcium index, as a function of the number of spots on the sun, you have a very good correlation between the two. So this index here is a proxy for the number of spots you have on the surface of the star. So on the sun, you know that you have the number of spots that change as a function of time, and this is the magnetic cycle of the sun. So this is real observation of one stars that we have been observing with HARPS over, I don't know, 10 years or so. And you see this variation as a function of time. So this is, we detect on this star a magnetic cycle. But then if you look to the radial velocity, you see a very similar trend here. So where this trend is coming from? So let's come back to this thing about convective blue shift. So all the star is blue shifted. And then you start to put one spot. So one spot creates some redshift there. Redshift, which means a positive radial velocity. And then you put another spot. You put more redshift. And you put another spot and more redshift like this. So more active region, more convective blue shift inhibition, so redshift, which means a positive radial velocity. And if you look to the correlation between this calcium index and the radial velocity, you see a very nice correlation there. And you can use this correlation to correct the data. So here on top, you have the raw radial velocities. And then here in the bottom, you have the radial velocity corrected just by this linear trend. So quite easy to correct for. It's perhaps not perfect, but it's good at first order. And then there is also another thing, is that because the velocity of the convection changes as a function of spectral type, if you go from G dwarf to K dwarfs and then to M, the velocity of the convection gets smaller. And therefore, if you observe K dwarfs or M dwarfs, the effect of magnetic cycle is smaller. So I don't know if it's good or bad, because if you detect it, then you can correct for it. If you cannot detect it, and then it's at the level of the precision of your instrument, it's perhaps more difficult. But this is another question. So yeah, so we really have all these different type of stellar signals that affect radial velocity measurement. For this is not too much of a problem. The blue stellar signals here. The green one, we have a few techniques already. It's really not perfect. I'm sure we can do better than that. But really, the big problem is active region here. So how can we model stellar activity if we want to find tiny planetary signals? Okay. So I did a test last year because I was a little bit, when I was reading papers, some different teams was analyzing exactly the same data set, and some team was saying, okay, on this planet, on this system, we have 2 planets. Some other team was using a different model to fit the stellar activity, the stellar jitter, and they would say, oh, on this system, we have 4 planets. And there is really some system, if you look into the literature, that have between 2 and 7 planets. So there is really a big change. And basically, all the teams are using different model to fit activity. So it seems that it's model dependent. And as Eric said yesterday, you should use different model and always arrive to the same solution. Otherwise, there is a problem somewhere. So what I did is that, so with all what I explained to you before, the signal from oscillation, granulation, stellar activity, I simulated some radial velocity data. And then I injected some planets in those data, and then gave all, 15 radial velocity curve to the community, and asked them if they wanted to analyze them and try to find the planets despite the stellar signal. Okay. And so this is a small summary, so it's a little bit complicated, I'm sorry. But basically, just look to 3 different colors. First is dark green, which means that the team have detected a planet, and this planet was in the data. So it's a good detection. Then there is the white here, which is a signal with a high signal to noise, but the teams were not able to detect it. And then blue here, it's planets that had a low signal to noise. So it's, if the team didn't detect this planet, it was a difficult case in this case. And finally, the red here, it's false positive. So the team said, we have a planet there, we are confident in it, but in fact, no planet was injected into the data. And there is several techniques that have been used here. So 2 teams use Gaussian processes, regression. 1 team used moving average. So there is 1 team using moving average. Okay, then apodized Keplerian, which is basically fitting wavelets to the data, and then some other teams that used more like classical technique like pre-whitening, filtering in the frequency space. And basically what you see here is all those techniques that are here in the bottoms are non-Bayesian technique with non-red noise models, and the teams here at the tops are teams that have used a Bayesian framework with red noise. And here you just have a difference in the size of those diagrams. I gave to the team 15 different radial velocity sets. And the big circles, the teams have analyzed the 15 data set. Smaller circle here, it's only 5. And the very small circle is only 2. So it's not so easy to compare between the two. But if you look really to team 1 that use Gaussian processes and team 3 that use moving average, it's basically the best result that you can get. And if you compare these two different teams, planets, so here, so I really defining the signal to noise, which is the semi-amplitude of the planet divided by the radial velocity RMS, and that normalized to the number of observations. And in fact, you see that there is a threshold of 7.5, where the signal that had a larger threshold than that, a larger value than that, was most of the time detected. Signal at a smaller value was much more difficult to detect. And so planet with this high signal-to-noise ratio, 70 to 90% of the planet were recovered in the data. And then when you go to smaller values here, you see that you do up to 20% or less. And then if you look to the false positive, the mistakes that the team have done, there is not so much in the end. So this team here, using the moving average, have done really a good work. And then it's difficult to know if it's really due to the moving average or due to the Gaussian process, because the team don't use the same framework. Some team have been working, or this team, it's the Tuomi team. They have been working on this moving average thing for now 3 to 4 years, so they know quite well how it works. This team just started to implement Gaussian process, so it's difficult to really compare. But I think one of the takeaway message of this challenge is that basically the teams that have used red noise models with a Bayesian framework where you can compare between models, so you can do a model only with your Gaussian process, and do a model with your Gaussian process plus your planet. And then you can compare the evidence between the two. And you can say if one is significantly better than the other. I think this is really the way to go. Okay. And so now, to answer to the question of Eric before, where that Deborah showed that you have to go to high resolution, very high signal to noise, and you need measurement nearly every possible day, and even better than that. So we started a small project to do that. And perhaps the only star where you can do that is the sun. So we built a small solar telescope to observe the sun every possible day. And then just the light of this telescope is fed to the Harp-Snow spectrograph. So we can get measurement of the sun for 5 to 6 hours every day with a cadence of 5 minutes. And this like all the year long. And no one uses Harp-Snows during the day. So we have full daytime. Okay. So the problem when you try to study stellar activity or the different type of stellar signals is that when you look to a star, you just see a point in the sky. And it's very difficult because you know that the effect is due to spots rotating on the star and so on, but you don't see them. So it's just impossible to understand. It's very difficult to understand. The sun, you have SDO, you have SO, you have plenty of satellites that are constantly observing the sun, and you see, you can know in real time what is the status of the photosphere of the sun. So if we can observe the sun, I think we can really learn something. So this is the small telescope that we built with people from the CFA, David Phillips, that is working a lot on Harp-Snows and the laser frequency comb. And this is what everything costed 20,000 20K basically. So it's not a very expensive project. But these are the data that we have so far. So 8 months of data, and we have nearly measurement every day. So we have some gaps here in the beginning because, of course, it was the beginning of the instrument, so we had some technical problems and so on. But now we are in a regime where nearly every day when there is no clouds, we can get a very good measurement of the sun. And in this case, there is just an outlier rejection. We just look to the flux that we have, and we just remove all the measurements that don't have a good flux just because there is clouds passing by. So those data are very clean once you remove just the data with a bad flux. And so you see the signal of Jupiter and Saturn, and you see that the signal is at 1 year, and this is because you detect the synodic period and not the real period of Jupiter and Saturn. So the periods are very close to a year. But once you correct for this effect, you are left with a residual with an error mass of about 2 meters per second. And you can see some variation here. And in fact, what you see is the rotation of the star because you have spots and facula on the star rotating with it. And this is just a Fourier transform of the data, a periodogram. And you see a huge peak here at the rotational period of the star and the second harmonic of it. So this is really the sign that we are affected by stellar activity. So correction techniques, so I will not enter too much into the details. But because we have really a lot of points there, we can start to use autoregressive techniques like Gaussian processes, for example, because they are really well constrained. And so here we just bin the data over 1 day. Okay, so we have one measurement every day, which is the sum of 5 hours of observation. And because the sun is rotating with a period of 25 days, during 1 day, the radial velocity of the sun due to activity doesn't change a lot. So it's why we just bin the data over 1 day. And then you can use like Gaussian process to regress those data. And those are the parameters that we injected in the Gaussian processes. So even in this case, we fixed the rotational period to 27 days. The coherence time, we fixed it as well to 27 days. It should perhaps be the double of it. We know that the active region on the sun have a lifetime of about 2 rotational periods, but okay. But even with those 2 parameters fixed, and then we fit the amplitude and these roughness parameters, once you remove the Gaussian process regression, this is what you get in the end. So I told you that before we had this 2 meters per second of radial velocity RMS, and then once you remove this autoregressive model, you are left with 30 centimeters per second. So it's perhaps not yet the 10 centimeters per second where you want to go, but the thing also is that our instrument has a photon noise of about, photon noise limit of about 20 to 30 centimeters per second, because the way we are observing the sun, we are losing a lot of light. Okay. And then there is also another thing that we are investigating with those data. So you can take image from SDO, and then from the different indicators that you have from SDO, you can see what you can separate from the photosphere the spots here in yellow, and around the spots the facula. And also SDO give you for each pixel of the image what is the velocity. This is an instrument called HMI. So then you can take all the velocity of the pixel, then basically weight them with the brightness of all the different regions, so spots or facula. And then you can arrive to a radial velocity for the sun, disk integrated. And then you can do also another thing, is that you can look to a minor body in the solar system, Vesta, to see the sun, what the reflected light of the sun on Vesta, as if it was a point, like a star. And then you can compare the velocity that you measure on Vesta with the velocity that you measure on the integrated sun with SDO data, basically. And this is what you get. So here on top, yellow is the data taken with halves of Vesta, and in blue is the data integrated of SDO image. And although it was not working very well at the beginning because they had problem with the guiding of the telescope, and then they were able to figure it out, then you can see that for the second period of observation here, the two data set matches quite well. So now we want to do exactly the same thing with the data that we have from the sun. And the thing is, because you have this high resolution of SDO, then if you see a small bump here in the radial velocity, you can say, okay, this is really due to the spot that just appeared at this time on the sun. And then you can try to improve your model of spots and facula. So just a small summary, the data that we have from this solar telescope, so sub-meter per second radial velocity precision. We have the long-term stability of HARPS, which is about 1 meter per second over several years. We have 4 to 5 hours of observation every day. So I think that at the moment, this is really the best data set that we have to study stellar signals. So we don't have the very high resolution like you would like, Deborah, like 300, 400. This is HARPS noise, so this is 115,000. But we have the high signal to noise. So we can perhaps go in a regime where we have these 3 different PCA components. And then the goals, of course, understanding stellar signals and finding correction technique to mitigate them. And this would be something super interesting to do, try to detect the signal of Venus on those data. Because Venus is very similar to the Earth. As I showed at the beginning, Venus is 10 centimeter per second. It's a little bit shorter in period. It's 225 days. And of course, we would prefer to detect Venus than the Earth, because we are rotating around the sun, if you do a small mistake in the barycentric radial velocity correction or whatever, you will be left with this 10 centimeter per second. So Venus is a safe case. And so I will end here and take some questions. What are we pointing? So first when we started all this, we thought, okay, we can just point the blue sky, and that's it. But the thing is that you have strong winds in the atmosphere, of course, and the light that are scattered on the particles that are moving with this wind velocity, you will have a Doppler shift due to that. So you cannot just observe the blue sky. So what we are doing is we are observing the sun directly. So we are taking an image that is 5 times the solar radius. And then there is another thing, is that you really have to be very careful that all the parts of the sun have exactly you really exactly get the same flux for all the different parts of the sun, because the sun is rotating with a velocity of 2 kilometers per second. So if you just put more weight on one side of the sun than on the other, you have big residuals. So then we just inject all this light, these 5 solar radius around the sun, inside an integrating sphere, which is a sphere where the light can bounce 1,000 times before going out. And by doing that, we really are able to be very stable in flux on the entire disk of the sun. And it's why we reach this. If we look to 1 day of measurement, we are at 50 centimeter per second, which is the limit of HARPS noise, basically.
Small changes aren't present.
So this is not night to night. This is, To which slide do you refer?
So I think you showed a plot where, you know, every minute there you had a new data point.
Okay, stellar oscillations. Okay, yeah.
So, I mean, one night I could see that, another night I could see something slightly different than that.
Yeah.
How do you know the difference between what the star is doing at that time scale and what weather or your local weather is doing at that time scale?
Yeah, so I would say that on these time scales, weather don't change so much in this case. And so now we have what? In Kepler, you see in photometry, you see all these stellar oscillations, so they are real. This is clear. And there is plenty of different radial velocity instruments on the ground and in space that are observing those stellar oscillations, so they are really real there.
Deborah?
What's the total number of observations that you've taken
Of the sun?
that are included in that data set that you showed us?
10,000 spectra. Perhaps 8,000 if you clean them, but it's something like that. So we start to have a lot of data. Yeah.
See that effect in the
Yeah. So
time during the day?
So what we do is that the question is because the sun is resolved in the atmosphere, one part of the sun will go through more atmosphere than the other, and therefore you should see an effect in radial velocity. So what we do to mitigate this effect is we really observe like 2 hours before noon, 2 hours after noon. But if we go to longer than that, we see a small drift. We see it like early in the morning, we see that the data are a little bit more like a little bit upper than 0, and then in the late afternoon there. And the effect is about 50 centimeter to 1 meter per second. But because we understand the effect, we can correct for it.
Last question?
When you showed that plot with a really nice picture of granulation, do you know about the temperature difference between the light bubbles and the dark channels between them?
So the difference between the granulation cells and around it the intergranular lane. So it's well, I don't want to give a bad answer, but it's like 500 to 600 Kelvin. So it's a big difference. It's really a big difference. And in contrast, is like 1 to 10 or something like that.
Is it also maybe a little bit more blue flux?
So is there a wavelength dependent of granulation? This is the question. Yeah, this is a good question, and I don't really know, in fact. I don't know if there is, does someone know if there is an effect of wavelengths on granulation? No? Well, at least it's not obvious, otherwise we would have detected, but perhaps at the 50 centimeter per second level, perhaps, I don't know.